Hi guys, welcome to Backend Engineering School, and in today's video we will be discussing about the concept of concurrency control. We will also understand the different types of locking mechanism. We'll go through the pessimistic locking. We will also go through the optimistic locking. We will try to understand the different kind of traits of, right? So you will get an idea that what are the situation where you can use the pessimistic locking and then you can use the optimistic locking, right? So if you are a candidate of computer science, or if you are already a developer, tester, or whoever working in a software organization, you might have heard this term concurrency control already. I'm assuming this. Even if you're not aware, that's okay. Let me try to understand quickly that what is concurrency control. So let's say assume that you have a shared resource, right? So that shared resource could be anything. For example, for a moment, let's assume that you have a variable x, right? And then there are multiple threads. You can use a terminology of threads, you can use a terminology of transactions, but the fundamental understanding is, for example, transaction 1 wants to update the value of x. So let's say x is equal to 10, right? Now you don't want, so while transaction 1 is writing a value to x, you don't want transaction 2 and 3 to also write the value of x till the time the transaction 1 gets complete, right? So the only way you prevent by doing this is you lock this resource. You take a lock on this resource, right? Now there are ways that we will understand, okay, what kind of locks and how can you acquire a lock on this shared resource. But the point is you need to lock this resource so other transaction won't be able to write on it, right? So what happens if they write on it? So let's say transaction 1 reads the value of x is equal to 10, right? And then what happens is transaction 1 is doing some kind of transaction and is doing the value x plus 20. So the value will become, let's say, 30, right? Because the current value of x is 10. Now even before that, transaction 2 comes in and then it performs x minus 2 and is equal to 8, right? Now before transaction 1, because of the fact that transaction was kind of longer than transaction 2, the value of x has become now 8. Now the value of x that transaction 1 sometime back when it tried to read it, it was value of 10, right? So the actual that the result value was supposed to be x is equal to 30. Now the value is 8, so it's still reading the incorrect data, right? So this kind of system inconsistencies can happen if you have a shared resource and you don't have a locking mechanism on it, right? So now we want to prevent this kind of system. So this is concurrency, the concept of concurrency, right? This is all concurrency. So there are transactions, or if you are in the software development, let's say there are threads, and if you are a person of database, you can use a terminology of transaction. Then how can you, there are different transactions, there are different threads running in a race to basically get access on the shared resource, right? Now which can lead to very difficult situations of inconsistencies, right? You could have a lot of difficulties with it. So in order to prevent these kind of scenarios, you have a concurrency control mechanism. How can you achieve the control in the concurrency, right? Because there could be concurrent transactions. This is where your concept of concurrency comes in, and this is where the concept of locks comes in, right? So where this particular article that I have written on suchet.substack.com, more specifically into optimistic locking, but in this video we'll also try to cover the optimistic locking, but in this video I'll try to cover the pessimistic locking as well, right? So if you see the types of locking, I'll come to this part as well, right? The optimistic locking. But if you see that the pessimistic locking, right? So pessimistic locking is very simple. So let's say you have a shared resource right here, and there are different transaction 1, transaction 2, and transaction 3. Let's say transaction 1 wants to update the value of a resource. A resource could be anything. Let's say if in the database, you can assume it's a row, right? It's a resource that different transactions want to update the value at. In threads, if you are doing some kind of multi-threading systems, or you are dealing with the concurrency you have an environment which is kind of multi-threaded. Yeah, there could be concurrency issues, so you might fall into the issues of threading, right? But the point is same, right? You need to perform the concurrency mechanism, concurrency control basically. Now in pessimistic locking is very straightforward. What happens is, for a resource, if a transaction wants to access, so transaction will go directly and try to acquire the resource, try to acquire the lock on it, right? And if the resource is available, it will get a lock on it. Now till the time transaction 1 has lock on it, none of the other transaction can access that particular resource. What it actually means is, till the time transaction 1 has lock on resource, only transaction 1 can perform the write operations on this shared resource. None of the other transaction can perform any of the write operation. Now that depends, right? So let's say if you are a person of Java, there are different kind of locks. If you are dealing with the software development, right, you could create a read write lock, you could only create a write lock. So different type of locking mechanism you have. But the point is that if a transaction or a thread have lock on a particular shared resource, only that particular transaction or thread can perform the write operations on it. Now what happens to other transactions till then? The other transaction will be on hold or will be in the waiting states, right? So pessimistic locking, as I said, and also as I discussed in here as well, very straightforward. You take a lock, update the value and come out. So now once you out, the other transaction will try to acquire the lock on it and then will try to perform the values on it, right? Now because of the fact your shared resource is not available till the time transaction 1 has lock on it, there could be some chances of performance degradation, right? For example, because now transaction 2 and 3 has to wait till the time transaction 1 gets complete. So that is why you could fall into the situation of performance overhead, right? And again, it reduces the concurrency as well, because see, the concurrent system, the basic nature of concurrent system is the concurrent transactions can concurrently access a resource, but here you see with the pessimistic locking, the other transaction cannot, right? Now because you are dealing with the different locks and all those things, you could fall into situation of deadlock. If you don't know about deadlock, that's okay, I'll try to quickly explain you, right? So now if I go here and then I will say okay, now if you go here and try to understand the deadlock, right? So let's say this is transaction 1 and then you have resource 1 here, right? And then you have resource 2 here, right? Now you have transaction 2 here. Now what happens is transaction 1 is accessing, making changes in resource 1, transaction 2 making changes in resource 2. Now as part of the transaction 1 can only gets complete once the resource 1 changes are over, and then it gets complete with the resource 2, right? But resource 2 is being held by the transaction 2. Now transaction 2, in order to get complete, it also need a transaction 1. So this guy also need this and this guy also need this, right? So transaction 1 is waiting, resource 2 gets free from transaction 2, and then transaction 2 is waiting to get R1 resource free from transaction 1. So both of these guys, transaction 1 and transaction 2, waiting for each other to release the resource. But in this particular scenario, you see none of the transaction is releasing the resource. Now this is kind of a bottleneck. So this particular scenario is known as deadlock, because you cannot move ahead. It's a dead end, right? And then there are different problems of concurrency as well. For example, many times you would have understood or heard the term of starvation. So what starvation means is, let's say you have multiple transactions, and then those multiple transactions want to access a resource R1, but because of some problem, because of the fact that transaction 1 is keep on using resource 1 and not releasing it, all these resources will be starving for resource 1 and will be on waiting state. So this is kind of a situation of starving. So if you want to understand starvation in depth, so let's understand, right? So let's say transaction 1, transaction 2, transaction 3 and transaction 4, and you have a resource R, which is a shared resource. Now transaction 1 acquires this resource and makes changes. The moment transaction 1 releases the resource R, transaction 3 acquired the lock on it, right? And then the moment transaction 3 releases it, transaction 2 acquired on it. When transaction 2 releases the resource, the lock on the resource, shared resource, transaction 1 acquired the lock on it. So you see, T4 never gets a lock on the shared resource in order to perform its update operations. So T4 is a starving thread or transaction. It's in the starvation state. So these kind of concurrency issues you fall into when you do not perform the concurrency control correctly in your application or in the database as well. It basically handles the concurrency internally, right? So as I said, there could be high chances of deadlocks, and also, when you doing a software development and you have a multi-threaded environment, you need to achieve concurrency in it. And if you are using pessimistic locks, you have to deal with a lot of locks, lock and unlock, lock and lock, timeouts. So all those things, the mixture of it makes a little difficult, right, in order to implement the pessimistic locking. Not every time, depends on the use case by use case, but in a general term, we can say that the pessimistic lock generally it's complex to manage, right? So that is why pessimistic locking can be avoided using some kind of different locking mechanism. And this is where your optimistic locking comes in. Right. So now let's quickly understand the optimistic locking. So by the term, you can understand that it's optimistic, right? So what I mean is, so if I go here, okay. So now this is where your optimistic locking comes in. And so now try to understand what is optimistic locking. Okay. By the term, you can understand that it's optimistic, right? So the point is, and logically it's not kind of a locking. You don't acquire a lock on a particular shared resource, right? What you do, you logically implement it by the means of the versions and all those things. We'll see that later in the part of this lecture. But the point is, the optimistic locking will not lock the resource from the beginning to the end, right? So what it does is, it will only perform a conflict check, right? We will see what is conflict. Now, even by the definition, if you see, it says that it does not lock the entire resource, right? From beginning, it assumes the chances for conflict are rare. So it only checks for the conflict only during before the write operation or the end of transaction, you could say, right? So by this diagram, you could understand there are transaction 1, transaction 2, transaction 1 and transaction 2. So transaction 1, let's say you have a resource with version 1. So what you're doing is, the one way of implementing the optimistic locking is using the versions, the different variations of same resource. So the way it will work is, transaction 1 wants to perform a write operation on your resource 1, right? So now it will read the data value first. So let's say it reads the value first, the value current version. The moment when transaction 1 trying to read the resource, the current value is version 1. The version 1, let's say you could say version 1 value, right? Now, when transaction 2 also wants to perform the write operation, so it also try to read the value of resource. Again, both transactions received the version 1 copy of the shared resource. Now, before transaction 2 transaction 1 wants to perform the write operation, right? So it finished quickly, and then when it written the new value of resource, it updated the version to version 2, right? So now we'll come to that. There is a point conflict check. We'll come to that point. Now transaction 2 goes in and it also tries to update the value of resource, a new value of resource, but it checks that the current version is not version 1, the version value that I was able to read at the time of read operation when it happens here, right? Now, so it identified that there is a conflict because the moment when I read the value, it was version 1, but now I can see the version 2 exists here. Now what happens is it's a conflict situation, right? So it will avoid doing the write operation, or to fix the situation is it will take the updated value and will try to update the new value. So if you remember in the beginning of the lecture, I said x is equal to 10, but transaction 1 updated x is equal to 8. Now what happens is the correct value of x 8. Now transaction 2 has to receive the correct value of x 8. Then how the correct value of outcome can be achieved. Now this is where, now let's understand, if this is not clear, let's understand using this diagram, right? Now what happens is, you have the value of x, you have a shared resource x, right? And then this is transaction 1, this is transaction 2. Now this guy read the value of x is equal to 10. Currently it's 10, right? And then this guy also do a read operation, it receives the value is equal to 10. Now transaction 1, or let's say transaction 2 finished earlier than transaction 1. So it updated the new value of x is equal to 8, right? So it was, let's say, version 1, and it also see version 2. Now transaction 1 goes in and will try to update, let's say it try to perform the write operation, x is equal to 20, right? When it going to update the value, it is x is equal to 8 in version 2. Now when it goes to update the value x is equal to 20, it sees the version 2 exists. That means somebody else has already come earlier and updated the value of x, right? So the value that I hold is kind of incorrect. So this whole process that it does, right, in order to understand if I'm still holding the correct value, is the conflict detection, right? Now it will realize, okay, I have the incorrect value, I don't have the correct value. So the correct way of fixing it, it will try to read the value again, read the value of x is equal to 20, x is equal to 8 again, and then perform its operation again. Now on the x value, because it's now correct new value, whatever the outcome will be, it will be correct, right? So all those issues that you were having because of the concurrency, you basically avoided all those issues. So this whole implementation is known as the optimistic locking, right? Now what you achieved by doing so is you enhance the performance, right? We'll come to that point, what are the trade-offs, right? Where you can use the optimistic locking, where you can use the pessimistic locking. We'll come to that point. Before that, let's also understand, although we have already gone through by the example, but formally let's understand how your optimistic locking works. Now, as I said, right here, both of these guys, right, they are reading the value. So it's a read phase. First, transactions or threads, they will read the value first. So both of these guys are reading the value, and then validation. Both of these guys have the value, they have performed the operation, now they want to update the correct value. But before that, they will validate. What is the validate? Conflict detection, right? They will validate if the version 1, the version that they hold, the transactions hold, is same as the version that exists with the resource, right? If that is same, then they will go ahead and perform the write phase. They will update the write whatever the new value is, they will perform on the resources, right? So this is optimistic locking, very very straightforward. You see, you're not locking anything, right? What you're doing is you're simply by logically you implemented the system in a way, so you are checking the versions, right? But by means of using some other variable, you're trying to understand that if you have the correct value or not. Now you see, as I said, that this will decrease the performance, because transactions or thread doesn't have to wait, right, for in order to access the resource. Now, but there is another problem. Now see, if you have a very high write system environment, right? For example, if you're dealing with any kind of retail system, or let's say any system, or let's say you're dealing with, I don't know, you could take any example, hotel reservation system or any system where you have a write operations, you have a lot of, which is a write heavy system, right? Those kind of scenario of using optimistic locking can lead to few problems, because you see, this involves the validation phase. So if you have a high write operation, there will be a high write request coming in. For all write operations, you will be doing the validation. Now validation, when I say conflict detection, this will lead to a delay. The whole operation will be costly operation. So now this is where it's not recommended for high write kind of systems. People also use a term of data contention. Data contention means you have a system where you have a write, maybe high write operation, maybe high read operation, or just cut this part. All right, so now there are, you see, by implementing the optimistic locking, you also reduces the chances of deadlock, because you're not performing any kind of locking, right, by means of software, by means of database, by any means. So you also avoid the problem of deadlocks in the system. So system becomes a little bit straightforward and easy. Now, but you need to remember that optimistic is not suitable candidate for a high write operation, as I said. So there are different trade-offs, right? If you think that you have a multi-threaded system and you won't get a lot of write conflicts, you can always go ahead and implement the optimistic locking. If you want a system which is very highly accurate, right, and you can afford enough, basically you are big enough to afford the complexity implementation, by means of implementation the complex, you can afford to have a complex system, you can always go for pessimistic. But again, if you want the high performance, you can always go for optimistic locking. So those kind of trade-offs involve. So there is no one answer. It totally depends, I would say, on what kind of system you have, what kind of requirement you have. Accordingly, you can select any kind of locking in it. But at least by going through all this, right, we understood that optimistic locking could be a good candidate over pessimistic locking several times, right, if you do not have a very high write system. So for this video, this is it, guys. Probably in the next video, I'll come up with some other topic. And how did you like about the so that's it, guys, for this video. This is it. I'll probably in my next video, I'll select some other topic, and maybe you can also comment in the comment section if you want me to cover any topic, right? So this is it, guys. Thank you so much.